11/14/2017, midway through November. It's the eve of the Ides of November. Who'd have thunk it? So this is all stuff we did. This is the first this is the first 4 slides. The others. This is all covered by the video that you watched. So we're not going to talk about it. You know that Mendeleev really is sort of the father of the whole thing. With contributions from Moseley, they found subsequent groups of elements, and Mendeleev talks a lot about this, periodicity. So let's move on to just terminology and getting that terminology straight. So this is terminology that we picked up in the last chapter, but we have to be really, really careful that we know it well. And in grading the tests, I would say that there is some confusion on some of it. When we say something like 1, 2, 3, those are energy levels, main energy levels. We can call them shells. We talk about them very often as n equals because we refer to the quantum number for the main energy level is n, is referenced as n. So that's a shell. When we say 3s or 2p or 4d or 5f, we're talking about a subshell. And we're talking about all the orbitals in there. So when we talk about 2p, that includes 2px, 2py, and 2pz. That whole thing is the subshell. This seems like, why are you focusing on this nitty-gritty? It becomes really important here. Okay, then we can break it down all the way to the level of orbitals. And at that point, we're saying, you know, the 4py, the 5pz, 3d2. Those are individual orbitals. 3d2 sounds like a robot that we never heard of from Star Wars. But anyway, those are individual orbitals. You're going to see in a second why this matters. Pull out. Excellent. So on the periodic table, and let me pop one in here. Don't worry, you're going to get one too. The groups run down. Groups go up and down. And many, many, many years ago, a physical science student came up with a mnemonic to remember that if you have a hard time with it, that gravity pulls things down, groups go down. That person would be in their mid-20s now. The periods are the rows that run across. I don't have a mnemonic for that. Feel free to come up with your own. Now, I want you to absorb this chunk of text. I'm going to read it to you. Length of periods is determined by the number of electrons that can occupy the sublevels being filled. Period 1 fills 1s, which holds 2 electrons, and there are 2 elements. Period 2 begins filling 2s. I'm going to give you a moment with that. Okay, so we're all on our blank periodic table. I've circled the first period. I put an X there. Van Brainer, Dr. Van Brainer, who's the guy who developed all these tables I use, you'll notice that they all say Van Brainer at the bottom. He does this weird thing with hydrogen, and we'll talk about that later today or tomorrow, but there is really no extra element there. So just so you know. This element, we don't have to know what it is. How many electrons does it have? 1. So where is it filling? 1s. 1. Okay. So then this element, and again, we don't have to know what it is. It's got 2 protons, 2 electrons. What's it, what would its ending configuration be? Oh, it'd be 1s2. Well, then if we move down to here, we add 1 proton, right? Because it goes up by 1 every single time, so we also add 1 electron. So this right here, I'm going to have to get rid of some of my funky lines here. This right here would have a 1s2, 2s, what? 1, right? Because it has 3 electrons. Does that make sense? Okay, I see some people who are crinkling up their faces. If you are crinkling up your face, talk to me. Start running again. We move over 1. How many electrons do we add?
Another
1. So then this would be 1s2, 2s2. Yes?
Mm-hmm.
What happens when we get to here? Where do we start filling?
The 2p.
2p. So this element, whatever it is, and it doesn't matter what it is. We don't need to know what it is. We know that we added one electron from the last element, so 1s2, 2s2, 2p1. And then the beauty of doing this on Doceri is that I can shrink that to fit it right. Well, that didn't work as well as I anticipated. I can't even find it. So when I add one electron in the next element over, what's my configuration going to be? 1s2, 2s, whoops, not ss2, 2s2, what? 2p2. That's convenient. Okay, what do we get here? This is like it sounds like a waltz. 1s2, 2s2, 2p3. Okay, maybe only in my head and not in yours. So I'm just going to say blah, 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 2p3. Then what would this be? Blah, 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 2p4. Blah, 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 2p5. Blah, 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 2p6. Okay. Oh, sorry. Did my blah. Okay, so there's a peculiar pattern. We add one electron every time we move over one. It is cool. Because guess what we do when we get to here? When we come all the way back, you guys you've never seen a typewriter with a return carriage, have you? Yeah. Oh, fantastic, because that's my best metaphor for this. We go, add an electron, ding, 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 chunk. We go back to the other side. When we hit the bing, chunk, and we go back to the other side, what's going to be our configuration here? It's going to be 1s2, 2s2, 2p6, 3s1. So this is kind of peculiar. Check this out. This ends, I'm going to do this in a different color. What does that end with? What? S1. What does this end with? S1. What does this end with? S1. If you were a betting sort of individual, what would you suspect that that ended with? S1. Oh. It is! After we have had our talk today, you will be able to look at this blank periodic table and just go, whoop! And you will be able to identify the electron configuration of something without knowing how many, without counting electrons, without doing anything else. It's the best party trick ever. Okay, only if you're at a party of geeks, but still. Well, the geeks probably all know the trick, so never mind. It's not a good party trick at all. But what do you think this ends with? S2. So if we actually wrote out this configuration, this would be 1s2, 2s2, 2p6, 3s2. What do you think this ends with? Well, let me get rid of a few things. Let me shrink this down at least. We would have 1s2, 2s2, 2p6, 3s2, and then what? And then what? 3p what? 3p1. Well, hey, look right above it. What did that end with? P1! That's crazy! What do you think this ends with? What do you think this ends with? P3! Guess what comes next? P4! P5, P6. Every single thing, and I'm going to get rid of some of this, in this row is going to end with something, 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 P1. Everything here is going to end with something, 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 P2. Something, 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 P3. Something, 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 P4. Something, 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 P5. Something, 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 P6. Cool. Let's get down to something a little trickier. shall we? Before we get to something trickier, we should go ahead and establish a few things. So group 1 always ends with what? Something S1.
Yeah.
Group 2 always ends with something S2. Now, of course, the names get kind of weird here. Group 13 ends with some level with an S2, and it ends filling a P1. So something S2, something P1. The next group, I think you get the picture. What happens when we get to the Ds? Did you draw the orbital filling diagram? Could you do that at 2 in the morning in your sleep, woken from a sound sleep with no coffee? I would hope so by this time. I think you could. Okay. So then if we hit the carriage return, fa-chunk, ding, and we go all the way over to here. Without counting electrons. Without counting electrons, can you write the configuration for that? Okay, do it. And I'm going to cheat a little bit. That's argon, right? What would be next? Argon, what? 4s2. And then, when we get to here, where do we start filling? 3D. So here we have argon, 4s2, 3d1. Guess what this would end with? 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10! How many electrons can we put in a D subshell? 10. Oh, well, that's peculiar. That's funny, isn't it? Okay, now let's take a look at the statement here. Main energy level. The highest occupied energy level is the same as the period. Let's go back to here. G, what's the highest main occupied energy level? I'm going to get rid of a couple of these arrows. What is the highest main occupied energy level for this element right here? It's in the numbers. 3, right? Do you see that? Okay. What period's it in? 1, 2, 3. Huh. What's the highest main occupied energy level for all of these? It's the highest main energy level in which they have electrons. It'll be outside the noble gas notation. Hold up fingers. 4. This one has stuff in 4. They all have stuff in 4s. 3d1 is higher energy, but it's not a higher main energy level. Guess what period these things are in? 4. Huh. Huh. So let's try something here. Well, I guess we could look at magnesium. 3rd period, highest main occupied energy level is 3. So now if you look at the periodic table, it has actual elements on it. Where is bromine? What is its highest main occupied energy level? So you don't want to be looking at your blank right now. You want to be looking at the one with actual elements. Okay, so yeah, this has 4. This is on 2. Now let's try another little trick. So we know that everything here is filling, ending with a what? Something, what? S1. Well, in the first period, what do you think the something is? Highest main occupied energy level is the same as the period, 1s1. If we go down to the second period, where do you think this is filling? 2s1, you know, something, 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 2s1. If we go down to the third one, what do you think it ends with? something, 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 what? Third period, filling S1, 3S1. If you go to the next one, something, 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 finishing with 4S1. This is revolutionary. This is so cool. You can grab a blank periodic table and you can go, you want to know the electron configuration of that? I'll tell you the electron configuration of that. And you can do it without counting electrons. I know, okay. I know it's not much of a party trick, but I think it's so cool. I'll be really impressed if you do it. Actually, you'll have to do it on your test, so you should just learn how to do it. Let's imagine this one. What is that last row, the noble gases? What do they end with? Something, 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 something S2, something P6. So this noble gas, whatever it may be, and it doesn't matter what it is, what does it end with? 4S2 and a 4P6. Now there will be some 3D, or there will be a 3D in the middle there. You know, that's okay. Do you understand why I see crinkly faces? There would be a 3D10 in the middle there. But do you understand that it would end with a 4P6? Because it's in the fourth period. It's in row 18, which means it's filling P6. Okay. Okay, so the periodic table can be coded into blocks based on what sublevels are being filled. In groups 1 and 2, what sublevels are we filling? S's. 1 and 2 are the S block. Groups 13 through 17, guess what we're filling? P's. That's the P block. Groups 3 through 12 are the D block. I'm going to shrink this because I'm about to show you something that will change your life forever on multiple levels. So okay, here's the S block, and I'm going to color code these, and I'm actually going to give you colored pencils, and it's a gray day, and it's a virtual Monday because you weren't here yesterday. So everybody could probably use a little time where we shut off the lights and I let you color and we hear the swishy, swishy, swishy of colored pencils. It's very soothing. And we have the D block out here in the middle. Swishy, swishy, swishy. Ah, it's a glorious sound. A whole classroom full of swishy, 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 swishy. Oh, so nice. Lanthanide and actinide series. Anybody ever felt sorry for these poor little elements that are stuck out here just because there's no room? I used to wonder a lot about them. They're the F block. So this is what I'm going to show you that's going to change your life forever. Okay, so the S block, this makes perfect sense. And you can color yours any color you want. These fill S1, S2. The P block. Oops. Remember, that's an extra weird hydrogen. The D block. Why don't the D's start until the fourth period? Oops. Why don't the D's start until the fourth period? Because when does the first D orbital fill? After 4s. Oh, look at that. So here we finish filling 3p, and we go over here to fill 4s, and then we go to fill 3d. Huh. Why don't the F's start until way down there? Let me color them orange to make up for the fact that they're so not talked about. Why don't they start until the 1, 2, 3, 4, 5, 6th period? Where does the first F start filling? 5D, 5F, 6S, 6P. Let's try that out, shall we? 4D, 5P, 6S. Oh, Look at that, 4F. So why is the F block all the way down there? Because that's where it starts filling. Once you have seen the long form periodic table, your world is changed, rocked forever. And it makes sense once you see the long form table, to me. So what I'm going to have you do is go ahead and get out some colored pencils, and you can swishy, swishy, swishy. I would advise you to color both your long form and the one that you're using every day that has the actual elements on it. Okay? So I'm going to give you some time to do that. Create a key for yourselves. What the heck? I'll even give you a few points for coloring. Oh my gosh. Not very many, but a few. Swishy, swishy, go.